In this video, you will learn about how to factor a polynomial completely. This involves factoring a polynomial in layers using different methods until it is no longer factorable. We can usually tell when a polynomial is not factorable when the expression is linear. In other words, the degree of the expression is 1. Remember, degree implies we are looking at the term with the highest exponent. Let me know if you have any questions in the comments below. And don't forget to subscribe so you don't miss out on future videos. Let's jump right in. So before we do that, a few problems, I would like to stress that always try and be on the lookout for whether what you're given has 4 terms, because more often than not, you are going to use factor by grouping. Not always, but most of the times, if you have 4 terms, just be on the lookout for that. Always in any case, it's super important to just see if there is a greatest common factor, if there's something you can pull out in advance because you're working with smaller numbers and it just makes life easier. Last but not least, always be on the lookout for quadratic polynomials where the degree is 2 or the highest exponent is 2. And in that, don't forget your 2 cases where the leading coefficient is 1 or it's not equal to 1. And a reminder, if a equals 1, it's the shortcut method. If a is not equal to 1, that involves factoring by grouping. So let's take a look at this quartic polynomial, or in other words, the degree or the highest exponent is 4. So I have seen students, they don't realize that the highest exponent is 4. They'll think in their mind it's a quadratic, so they could, do the factor tree of a times c and yada, yada, yada. So just really, really make sure that you're paying attention to the exponents. So this is not a quadratic polynomial. It's a degree 4 polynomial. So really our methods are down to whether we could use factoring by grouping, which in this case we cannot because this has 3 terms, not 4. So last but not least, we're going to try our last tool in the toolkit. It's the Gcf method, right? And I do stress this is clearly not sum or difference of perfect squares and cubes, right? Okay, so we're going to have to see if it has a greatest common factor, and in this case, it does. So what do every single one of these terms have in common? They are all divisible by 2, and they all have at least 2 x's. In other words, I can pull out an x squared. So the greatest common factor is 2x squared. Let's do it. So reminder, when I pull out the greatest common factor from each term, it's like doing the reverse distributive property. So ask yourself, 2x squared times what gives me 2x to the 4th? X squared. 2x squared times positive 4x gives me 8x to the 3rd. And then 2x squared times a positive 3 gives me 6x squared. Okay, so now all we've done is factor out the 2x squared. Now again, if the directions say to factor completely, you have to see whether what we have going on in here is also factorable. If it's not factorable, then this would be your final answer. But you always have to keep going. So how do you know if it's not factorable? Again, you have to just go down your list of tools, right? So in this case, we can say, hey, this is a degree 2 polynomial. In other words, this is quadratic. So we do have some trick up our sleeves, right? This is definitely not this is not a difference of perfect squares. So remember, our 2 cases is either if the leading coefficient is 1 or if the leading coefficient is not equal to 1. Really, we could use the same methods for both, but if a equals 1, it's just, there's a shortcut to it. So it just makes life easy. So in this case, the leading coefficient is 1, right? So what else is true? B is positive 4 and C is positive 3. Okay, so how do we factor a quadratic polynomial where a is positive 1? Same thing as if a is not equal to 1, very similar steps. So we do a factor tree of a times c, which is 1 times 3 or just 3. paying attention to the signs. Yes, I know 1 times 3 is 3, but people often forget that -1 times -3 also equals +3. And we have to add each pair to see which one adds up to the b term. We want a +4. 1 plus 3 equals +4. So those are going to be the chosen factors. What's nice about the leading coefficient equals 1 is that we can now just take those chosen factors and plug it into our template. So that's a +1, so I'm going to write +1. And there's a +3, so I'm going to write +3. Now, could I have written x plus 3 times x plus 1? Sure. And often people forget to copy that greatest common factor, or else you change the problem. And this is our final answer. How do we know it's our final answer? So when the degree is 1, when the highest exponent is 1 in each of those expressions, that's an indicator that you can't factor out anything else. And we're done. Let's try this one. So you have to go down your list of tools in your kit, right? So we have factor by grouping. In that case, we need 4 terms. Is there 4 terms? No, so we cannot use factoring by grouping. In fact, there are only 2 terms. And with 2 terms, actually technically, right, we see this as a degree 2 polynomial. In other words, it's quadratic. The highest exponent is quadratic. So you could technically rewrite this as 18x squared plus 0x, right? Because 0 times anything is 0. So that middle term is technically not there, but totally valid. We can do this. So if you really wanted to, you can absolutely do the other methods, right? You can do the a times c, 18 times -50, and do the factor tree and yada yada. But hey, that's quite the large number there. So there is a very much easier way to do this. So notice it's 2 terms with a subtraction. So oftentimes when you do have 2 terms and there's a subtraction, you have to ask yourself, ooh, is this a difference of perfect squares? Now, it's the difference part is there because there is a subtraction, right? 2 terms could be difference of perfect squares, not always, but the only problem is that 18x squared is not a perfect square and neither is 50. But we haven't, I always say right from the very beginning, always be on the lookout definitely for the greatest common factor. So you're always going to be looking out for this definitely for sure. Definitely, and I'm putting a star next to it. So do those 2 terms have something in common? Yes, it does. They're both divisible by 2. So if I pull out a 2, now we end up with 9x squared minus, oh, not 9x squared. I am just kidding, making sure that you are paying attention. Oh, wait, I am just kidding again. 2 times 9 is 18. And 2 times -25 gives me -50. Perfect. Okay, so now what have we done? We've pulled out the greatest common factor. Hey, would you look at that? We have difference of perfect squared. Okay, so don't forget at the very end, when you're done, you better put that 2 in front. Don't forget about that GCF. Okay, so from here, we figure out our a and b. A is the square root of the first term. What times itself gives me 9x squared? 3x. And b is the square root of the second term, or the square root of 25, which is 5. Okay, again, so people might get thrown off. So technically the second term is a -25, but when you have difference of perfect squares, you're just looking at the spot it's in, right? And then you're just subtracting them. So in other words, difference of perfect squares, your a and b should always be positive. Anyway, so now we have a's and b's and just plug it into our template here. So it doesn't matter which way, oh, actually I take that back. So you can either do 3x plus 5 times 3x minus 5, Or you could just switch these two parentheses around. You could do 3x minus 5 times 3x plus 5. The only thing I stress is make sure you write the a term first, okay? And this problem would not be complete if you put that greatest common factor back in the game. That's our final answer. Let's do a monster review problem. Why is this a monster problem? Because it's going to review a lot of tools in your kit. So first things first, is this a degree 2 polynomial? That's definitely something you should always look out for. And it is not. The degree is actually 5. The highest exponent is 5. So you cannot use the two methods, right, where a is 1 and a is not 1. That's out the window. Next, is there a greatest common factor? There's nothing that every single term has in common. Okay, so we're not going to use the greatest common factor yet, right? So the next thing you should ask yourself, does this have 4 terms? Yes, it does. So when something has 4 terms, most often than not, it is factorable by grouping. So let's do that. If we assign our two groups of 2, will this work? Right? So when we do use factor by grouping, it does involve knowing how to use the greatest common factor method. So if we take out an x to the third of the first group, we're left with x squared minus 4. And if we take out a negative 4, oh, we can even take out actually something larger, can't we? We can actually just pull out a negative 8, right? And if you pulled out a positive 8, you'll see that the expression inside the parentheses don't match. So that's how you'd know, okay, let me try a negative 8. So when you do that, you end up with matching expressions inside the parentheses, which now that indicates this is factorable by grouping. Because now when we pull out an x squared minus 4 from each of the two terms, we are left with x to the third minus 8. Okay, so remember, this is a factor completely problem. So we have to see if each expression inside each of the parentheses is factorable. Now you might have noticed right away that this first expression is a difference of perfect squares, and the second expression is a difference of perfect cubes. So how about you press pause, you try this out, and then press play again to see if you got it correct. Worst thing in the world is you got it wrong. Oh, boo-hoo. And then you keep trying and eventually you'll get it right. Okay, so here's my difference of perfect squares. In this particular one, a is the square root of x squared, which is x. B is the square root of 4, which is 2. And in this second group here, in this particular case, a is the cube root of x to the third, which is x, and b is the cube root of 8, which is 2. Now, in this particular example, we happen to get a's and b's that actually are matching, but that's not going to happen every time. In this particular problem, it just happens so beautifully. But more often than not, you actually might get scenarios where the a's and b's are different. Just make sure you plug in the correct a's and b's in the correct formulas. Okay, so if I do the difference of perfect squares, that's just this template, right? X plus 2 times x minus 2. Just make sure you write the a term first. And then if I were to use my difference of cube root, difference of cubes formula, right? So this one is the minus plus plus. So that's going to look like, so I'm looking at this a and b. It's going to be a minus b, so x minus 2, times the quantity of a squared, which is x squared, plus the a times b, x times 2, which is 2x, plus the b squared. 2 squared is 4. So if you recall from my previous lesson, whenever you do a difference of cubes or sum of cubes formula, the quadratic expression is never factorable. Now, if you forget this, it's not a big deal. If you try and factor this quadratic polynomial, you'll find that there are no factors of a times c that add up to b. Okay, and so we're done, but the last thing that some people might like to do is you notice that the x minus 2 is written twice. That is the same thing as x minus 2 quantity squared, right? So some people might like to feel fancy and write the answer like this, but it doesn't matter. I hope this video helped you learn how to factor a polynomial completely. If you are interested in other factoring methods, I'll leave the links to those videos in the description below. If you like this video, make sure to subscribe to my channel right now. That way you don't miss out on my future videos like this one. Just click on the subscribe button.